In this lecture, we will discuss the topics about semantic web and linked data. Semantic web, or the technologies of semantic web go on another step of capabilities for searching the web, because we would like to search the web not only based on low-level information like keywords or just links between pages, but based on the semantics of entities that appear in the text or in the content generally. And we would like to represent the semantic information right in the web pages or in the web space. We start with the syntactic, so-called syntactic web, moving to the semantic web. But semantic web is a kind of illusion. We better speak about technologies for semantic web, because the particle technologies are successful, but the construction of semantic web is more in the sci-fi stage, because we cannot just say today we have semantic web, but we have some more or less successful technologies for making parts of the web semantic. So when we speak about the web as of a graph of web pages, web documents, we mostly think of the basic infrastructure. So we have documents that are encoded in HTML files. So these are pages, are documents, and we have the graph structure because these documents are linked together. And the search engines use this low-level information for searching. So we already discussed the information retrieval models, Boolean model, vector model. Both of them use the keyword extracted descriptors of documents. So there is just simple statistics extracted from these documents. And for PageRank, we just use, or PageRank uses the topological information on the web structure. So just counting the inlinks, outlinks, and distributing the PageRank. But we didn't really take into account some semantics behind the keywords, or something that is external, some background knowledge. This is something very difficult to manage at the really general infrastructure level. So we will start with the syntactic web, which is where we are, and we'll try to introduce some or present some technologies that go more towards semantics of data on the web. Okay, of course, we must distinguish between the web as an infrastructure, so general web, general search engines of HTML documents, and application on the web. For example, we have social media applications like Facebook, and in Facebook we have completely different level of semantics of data. On Facebook or other social media, Twitter, Instagram, YouTube, whatever, we have already very semantic information entities like profiles, posts, comments, likes, follows, whatever kind of interaction, and this is already very semantic, but it's closed in the application. So this is something that is not public to work with by other application. It's closed. So we are now concerned with the infrastructural level of web, not by web applications, and try to analyze these problems on this very general way. Okay, what would we like to answer instead of simple keyword queries would be, for example, this query that asks for houses on sale that are located near New York and are cheaper than the local price or average local price, and the houses are not made of wood. So this is a very complex free form query that doesn't or is not easily translated to some vector query, because in vector query we just use cosine measure on the histogram or on the vectors that basically consists of weights of terms for the document, and it is not exact query. But in this particular query we are basically trying to issue SQL query, but in using natural language, not using the SQL statement. But basically this is something what we would like to obtain, the information like based on SQL. But we have no database scheme. There is no database scheme on top of internet, on top of web. There are no attributes strongly defined, nothing like this. So how to basically prepare technologies that are able to answer queries like this? We are in completely different situations than with relational databases, because in relational databases we are limited to a certain information system. For example, eShop. In eShop we can observe properties that the eShop is closed. It's quite small in the domain because it sells some products. It could be managed and administered centrally because there is one central database of products or something like this. There is a limited number of use cases for using this database and so on. But on the level of web, we have very different situation. So realizing or preparing a technology for answering precise queries like that in so heterogeneous environment like web is very difficult. It's completely different story. However, the original idea of web that was founded by Tim Berners-Lee actually was so ambitious and expected the semantic web goals. So even the first idea of web suppose that there will be information that is machine readable, and not only machine readable in the sense that the documents could be parsed. Of course, in this very low level sense, web is machine readable, but only for rendering web pages, for the presentation layer. It's not machine readable for understanding the information and for reasoning about information. We cannot just use a web page to understand data, understand information on that web page. We can just read it, parse it, print it, show it, and that's it. And the search engines also reflect this. The search engine only parse the text, count the frequencies of the keywords, count the links between the pages, and do some basic statistics, and that's it. And all of the retrieval is based on this simple statistics. Not much of semantic reasoning. And this is what is the idea of semantic web. In 2001, which is almost or more or less 10 years after the foundation of World Wide Web, Tim Berners-Lee published an article in Scientific American, which is a popular magazine, where he mentioned again the philosophy of semantic web, but adjusted to the reality in 2001. So in that article, the semantic web was defined as an extension to the current web, that was not semantic, by technologies that enable computers and people to work in cooperation. So that means information must be well defined, machine readable, and allowing to understand information in the way people understand information. by the simple web as it is, just the presentation level. But how to do that? First, we need to conclude or summarize the features of the so-called syntactic web. Syntactic web is just the opposite of semantic web. So let's name the normal web of the low-level structure of web pages as syntactic web. So the syntactic web is just focus on presentation of information. So we have web pages. The pages are documents, more or less. The documents are formatted, so we have some presentation markup on the web pages. We have hyperlinks in web pages, so we can see the whole web as a hypermedia. Hypermedia means a huge object that consists of many sub-objects that are linked together. So it's hypermedia, could be viewed as a digit library of interconnected nodes or interconnected objects. Also, it could be viewed as a database, as a graph database, but this database is not formatted because the nodes in the graph database do not comply to any schema or nothing like this. We can also view syntactic web as a platform for sharing multimedia, as a platform for applications, and of course some basic functionalities like keyword search engines, and also very important, it was the first level for information representation and unique identification. So syntactic web introduced the URLs, or later URIs, unified or unique resource locators or identifiers for locating worldwide entities. And it is, of course, basic infrastructure for linking media and people outside of the applications that also live on internet, on web. But on the syntactic web, it is very hard to answer background knowledge dependent queries, such as this one, where we want to find all the books of genre sci-fi where the plot doesn't include a spaceship. This is quite a complex query and difficult, because we cannot just rely on extracting keywords from this query and matching these keywords using, for example, Boolean model to the documents, to the web pages, because even that we can formulate a Boolean query for all documents that do not include the term spaceship. There could be different term for spaceship, or there is not explicitly mentioned sci-fi as a term, because it's about the semantic, about the genre. It's not about explicitly mentioning the word sci-fi. So from this point of view, it's extremely difficult to alter traditional search engines to answer queries like this, because we need some background knowledge about what we want to search, and how we infer knowledge from facts that are stored somewhere in the web pages or in documents, in content. It is also hard to ask data repositories. For example, in e-shops, in e-commerce, it is easy in the application. If you have e-shop, it's easy to really ask for the best hotel for my vacations that is close to the beach and is cheap, because this is the interface of an e-shop, of an application. But this is closed application, and we cannot just use Google to ask the very same question and obtain the same answer as would the application do, because Google, or search engine generally, is a universal search tool that is not bound to any domain, to any application, but in this case it should work the same, and this is not possible for closed applications. It's not possible from two reasons. First, the e-commerce companies would not disclose the data repositories that are hidden beyond some GUI, and also there is not specified a unified model for answering these types of questions. So first we need to model the semantics, and then we can use it. So we don't have the access and also the model for the semantics. So this is something that we would like to introduce, or to slowly become to discover this lecture, how to model the semantics. And therefore it is hard to also delegate such a task to a web agent that would basically solve the task, so answer the query. So let's say search for 2 days and book a hotel for me. So it's not really easy. And why is this so hard? I already mentioned the reasons. We need some background knowledge, and this is something that the algorithms based on the simple models don't have background knowledge. There is nothing like background knowledge in vector space model, and but the users, the human users have background knowledge, so they can reason about presented information that is presented to them as to human users, but the computers don't have this, so they cannot basically infer knowledge. Just suppose this Amazon web page. There is a Kindle wireless device, and you can see that this page is optimized for human reader, because we see many different pieces of information about the Kindle reader. We see the picture of the device, we see some basic description, the price, we can see the possibility to put this product into the cart, we can see some available accessories, we can also read some reviews on the product, many different pieces of information. Of course, this is meant to be read by human reader, not a machine. Machine can render the content of this page, but it could hardly understand it without any other support. And why this is so hard? Nobody says what is the structure of this page. So for computer, there should be some schema defined that would enable to convert this unstructured layout of information into some nicer formatted data structure, like to relational database. Of course, it could be converted to relational database, because I can have one product with some attributes here, and I could put it into a relational database. But how can I recognize it by some algorithm? I can recognize it as a human, but it's really hard to write an algorithm that without any training could really pick the right pieces of information and put it into a relational database. And there are other factors. First, the e-shop or e-commerce providers do not want to provide the data to be exported outside and be available, for example, to comparisons or mashup services that compare different retail businesses. So they do not support any other than end user presentation of their data, and also the layout of this page could rapidly change, just to prevent automated extraction of this information. So basically it is very hard to implement a search engine that extracts information on some more sophisticated level than just keywords. Of course, keywords you can easily extract keywords from here, but it is much more difficult to extract structured information from this page, because it changes all the time. Yeah, and this is why it doesn't work. We just use keywords, not structured queries, and so on. If we want to introduce some semantization or some semantic tools for the web, or for something that is called semantic web, it is often displayed this pyramid that consists from the very low level tools to the very high level. On the bottom of this pyramid there is two components, it's Unicode and URI, and this is the very basic assumption to actually start with any representation of information that is semantic. First of all, in the mid of 90s there was Unicode standardized, which nowadays seems basically automatic, but at that time it was quite a huge achievement, because it standardized the representation of characters worldwide. So in Chinese or North American, Slavic languages, whatever, Unicode does support unique representation of alphabets, whatever languages, whatever codings. So this was very important step towards representation of data as such. Then with the web, there came the URLs or URIs, unique resource identifiers or locators, that enabled to identify uniquely resources worldwide. So we had two things: the coding of the information, then URI. So these two were the very basics to start to build some global data space that is identifiable and searchable, and that could be arranged in a way that could be used for semantic web or searching for semantic information. Then the XML came again in the mid of 90s. Basically XML was inspired by HTML or earlier by SGML, and it was inspired by HTML in the way how the information is structured. We can see that in HTML we have predefined tags for representing and structuring the data. So for header 1 we have h1, and the markup is such that we have this beginning element and this ending element. Everything inside is the content of this element h1. We can hierarchically put more elements and nest elements, but their semantics, we are now talking about semantics, is predefined just for the presentation reasons. So h1 means when rendering the page, this text will be bold and huge. Then we can have here unbulleted lists and list item 1, list item 2, and this only means that these two lines of text will be formatted as a list, nothing else. But it's something good here. That's the hierarchical structure. So the markup is very simple, and what if we can generalize this system of markups to something that is more general? And we come to XML. In XML we can, and that's also the name, the acronym is Extensible Markup Language. We can basically use the same system of markups, but using whatever arbitrary markups as we want to use. So there are no predefined so-called elements. We can define our own elements and even attributes here, and generally content. And we still have the hierarchical structure of the document. The XML is is classified as a semi-structured data type or semi-structured format for semi-structured data, because it allows to capture structure, which is the tree structure here, or even graph structure, but also unstructured data like text that is inside, freely located inside the nodes. So we have semi-structured data. Besides the XML itself, there are other tools again based on XML, because in this way we can define very arbitrary documents based on these markups. And if we want to put some nice shape of the data, we would like to constrain the data by something that was called database schema in relational databases. But here we don't have any relational schema, but we want to have something like this. So there are tools like DTD or XML schema that allow to restrict the form of the information to some defined shape. Of course, this constraint or the restriction is not so heavy as in case of relational databases. Just consider about relational database. You have tables, and the tables have records, and the records have some values based on the attributes they are supposed to evaluate. And this is very strict restriction, because nothing else than the allowed values are allowed. So it's always flat structure with the data types that are supposed to have the attributes. Here in XML schema or DTD, it is more flexible. You can define very strict schema on the same level as the relational, but you can also say, okay, let there is only weak constraint on, for example, the maximum depth of each of the branch that is within the XML tree, or anything between. So it's more flexible. As I said, the names of the elements in XML documents could be arbitrary, and therefore it's highly extensible. That's why XML extensible. Possibility how to represent data. And for the semantic web technologies, this is very good container format to basically represent data that is structured but allows domain-specific applications on top of the element just as a container, or just as a general format for representing data. So, in this sense, XML is almost machine readable, but it is almost machine readable because it doesn't carry the semantics of the data. It only carries structure of the data that is separated from the presentation. This is the value on top of HTML, because in HTML we had some structure, but this was bound to just presentation. Now in XML we have data that is structured and is completely independent on the presentation. But the names and semantics of the text remain a problem because they are not connected with any particular semantics, and there is no global agreement on naming of various elements and their semantics, and basically this cannot be done at global scale because the web could be viewed as a huge distributed database that is not administered centrally, so everything lives very independently, and it cannot be just tied into one scheme or something like this. So this is not a problem of scalability. This is problem of the basically paradigm. So in web we cannot have scalable global schema. Okay, so what to do now if we can't have any schema? How to basically make something that provides the features of a schema, basically, because using schema we are able to understand data. Without schema in database we don't know what are the attributes, so how to understand data without schema? Well, we must go, as in many cases, here this is also the case when the top-down development or design doesn't work, that means from very global schema starting, this can be done, but it works the other way around. So if we are able to solve particular tasks from the bottom to up to top, we can do something, and we can build piece by piece something that is more and more semantic. XSLT, again, this is one tool for XML. As I said, unlike HTML, in XML we don't have mixed together the content and the presentation, but we can easily create an XSLT script to format data that are stored in XML document into HTML, for example. And so this is not an obstacle, this is just an option that we could use or could not, and for us it is just a proof that separating data from presentation is a good step towards semantic web. What is very important to understand or to register is namespaces. Namespaces such as namespaces in programming languages is a very powerful system for using names in different contexts. So the same as in, for example, C++, we can have namespaces in XML, and we can use the same name for an element in different contexts of different namespaces. This is very important shortcut for the creators of information using XML, because it's also human readable, not only machine readable, but namespaces serve for human readability. A namespace to be uniquely identified is therefore unified by an URI or URL, Uniform Resource Identifier, such as this one, and using the unique identification we can uniquely identify also the namespace. So this namespace is related to XHTML, and everything that is named inside this namespace is semantically connected to XHTML. This is a quite crucial point, because this is basically where the semantic interpretation basically comes into play. Because, for example, here we have some example. We have XML namespace defined as X, and this X namespace is identified using this URL. And within this namespace X, we use here the element called P. But the P is not any P. It is P in the semantics of the namespace X that is given by this URL. So even that the XML itself, when read and parsed by some general application, cannot interpret P as something that carries some semantic, we can still find the semantics using the namespace, because we have the namespace here, and at the address of the namespace, basically that's the identification of the semantics of the namespace. And this, exactly in this way, it would be used in the technologies of the semantic web. So namespaces are extremely important for semantic representation. Okay, so we still see the pyramid, and we are here. We have XML namespace, XML schema, but this is still not enough. So XML provides us the way how to, or the very general infrastructure, how to store structured data, how to define names of nodes within some namespaces, and the namespaces somehow must represent the domains for the semantic interpretations of the namespace, but this is not enough. So we need something more. We need some ontology and something that is useful for representation of facts, because we will use ontology as some common vocabulary for understanding the semantics that is connected to some concrete problem, to some domain, and we need some storage format for facts that basically serve us as the database. So RDF is a graph format for representing triplets, and these triplets are used to be could be composed into a graph structure, and we get basically a graph. Okay, so on top of XML we need two things: ontology and the repository of facts. Now, why ontology? Ontology in computer science, basically because ontology is quite overridden term. In computer science, ontology is some formal specification of knowledge as a set of concepts within some domain, and the relationships between these concepts. But what is more important and extremely important for us is that ontology means some shared base or shared vocabulary of concepts that are to be used in some functionality. The vocabulary. If we have vocabulary, let's have just simple vocabulary, like from English to some other language. The vocabulary is a structure that is shared by people, and it allows to say the same semantics using two words. That's how we use a vocabulary. But even if we have just one language, just English, we still need some vocabulary, just for people need to share information. If we the language itself, English, for example, consists of words and terms that other people agreed the semantics on. So if I say I sit on a chair, everybody knows what I'm doing because everybody has the shared knowledge of what is a chair and what is sitting. So this is some very, very basic interpretation of what we need. We need some shared vocabulary. But in case of a semantic web, we need something more than just a common shared vocabulary of English terms and their descriptions. We need something that is extensible. So we need something like ontology, which means we need some formal specification of concepts and some structure on top of that, some relations. Okay, and of course we do not need this, or we cannot do that globally, such like the English vocabulary, but we must do this specific to some applications, because there are too many semantic notions to be taken into account that this is impossible to make globally. This is basically the same as making the whole web semantic just globally from by the top-down design, which we already discussed. This is impossible. So the same for ontologies. It is feasible to create application-specific ontologies that provide some relations between concepts, and so allow some semantic functionality like inference and so on. And once we have ontologies, we can use them in organization of information and the semantic web basically tools. One of the simplest ontologies that students at the elementary schools meet with is the taxonomy of living beings, which is very simple tree that we have the specialization generalization relation, where living beings are split between animals and plants, and animals are vertebrates and invertebrates and so on. So this basically is obsolete taxonomy because with the discovery of DNA, this doesn't it is not valid anymore, but it is a nice example of simple ontology. In real world problems, this simple tree-based ontology is not enough, so we resort rather to graphs, not just simple trees, and the graphs are not just simple graphs, but multi-graphs. So, for example, we can start with this nice tree for some application in business, where we have the generalization specialization relation of these elements, but we could have another layer of ontology, and that means different type of the relations. For example, we have employee, that is manager, and manager could be either program manager or project manager, and the program manager funds project manager. So there is another link between these two. We can have other link that expert advises. So we have already three types of relations. We have the generalization specialization here, we have funding here, and we have advisory here. So it's already three. Then we have another root. There is not just one root, and so on. So basically the ontology could be much richer than just a simple tree. It is probably some multigraph. And on top of the ontology and the facts that we want to represent, it is also favorable to have some mechanism to reason over the ontologies. And for this reason or for this task, there are descriptive logic used mostly, which are some fragments of the first order logic, but also contain something that is more expressive than first order logic, for example, transitive closure. And these logics then allow us to infer new knowledge out of old facts. For example, if I have very simple example that I have a fact that X is an author of Y, then I can infer the inverted form of that Y is written by X. That this is really a simple inference, supposing that I can invert meaning or order of this relation. Another example could be using transitivity. If I have two facts, X is supplier to Y and Y is supplier to Z, then X and Z are part of the same supply chain just because of transitivity. For representation of facts, there was RDF standard introduced, that stands for Resource Descriptor Framework, and was standardized by W3C consortium, that allows to generally specify facts that are composed of triplets. There are multiple or many serialization format for RDF, and to be consistent with what we already introduced, it's also beneficial to use XML for RDF. So it's data format, but it's defined on top of XML, or could be on top of XML. It could be N3 and triples. There are other serialization formats, but we can everything represent by XML or extension of XML. So we can define scheme of RDF, but basically on the bottom it's XML. But what's important about RDF is that allows to define statements about resources. So every RDF document consists of set of RDF triplets, where each triplet is a form subject, predicate, and object. And it allows us to state some fact about some entity. So if we have entity New York and some value here and I, we can define a relation between New York and Y. So we are saying here New York has an abbreviation of NY, where New York is just a string. Here we can see that it is not entity here in this RDF triplet, but here it's really string. NY is again a string, and has abbreviation is a type of property. So basically type of edge in a graph. Of course, this isn't enough to be to just use strings here, because the string is just string. It has very low semantics. It is just string. So if we want to represent not string New York, but actually entity New York, which is basically the state New York or the New York City, we need to identify the elements here by the global identifiers. So using the URI. So in practice, we are using the namespaces, and these are translated into the elements within the namespaces are translated to the unified unique identifiers, but it could be also the constant. And then we have system for identification of all elements at the global scale. This is the grammar for RDF in the RDF XML format. And what we can do with this is, for example, in this example, we would like to represent this fact. And the fact is a web page about Tony Benn is published by Wikipedia. And we can transform this fact into two RDF triples, where the first one says that the particular web page, what we are talking about, is in relation with string Tony Benn using relation type has title, and the same page is in relation with string Wikipedia by this type of relation. And in the RDF XML format, we can represent it like this. We can reuse the feature of XML that it is hierarchical representation, so we can state the shared piece of information just once. This is the web page, the same web page as here. So we use in the namespace of RDF, which is this one, the element description. We already have the semantics for description in the RDF, but we can say that we use URI for the web page. So in the web page is not represented as a as a constant, but as an identifier, which in this case is the URL to the Wikipedia page. And to this web page we represent two facts, one of this triple and one of this triple. This first triple means that we have associated the web page with string Tony Benn using the relation title, has title, and the same page is associated with the string Wikipedia using the relation was published by here. All of the semantics of these nodes are defined within the namespaces. So this is important. Information we need to have in mind that basically the semantics is hidden in the namespaces. Here we can see that the Tony Benn and Wikipedia are constants, are strings, but we can easily represent them by another unique identifier. So if Tony Benn is not just a string, but it is really a named entity, that's called named entity, that it is not just a string, but it has an ID, then we would use not Tony Benn, but the ID for Tony Benn, and not Wikipedia, but the ID for Wikipedia. So this is the matter of choice. So this is how RDF triplets can be represented in the RDF XML format. The RDF scheme, basically, or the RDF language, consists of many classes and properties, and you can see that all of them are within the namespace RDF, so we are still consistent with the XML notation, and we can further extend or limit the data stored as XML RDF files using another schema that is called RDF schema. So the same way we can limit XML documents using XML schema, we can do the same with RDF documents, RDF repositories. So we can limit or allow specific application-dependent classes and properties. So this is for us basically the application-specific restriction of what we represent using RDF. And together we can use RDF and RDF schema for application-specific representation of facts. The RDFS is basically an ontology for us, and the RDF is basically the facts that we represent. And we can show it here in this scheme. We have visualized the facts that we have. We have the schema, RDFS, and we have the data, that's RDF. So we know from ontology here, given as the RDFS schema, that if we have instance of writer, then we know that the writer writes books, and we have that check writer is a subclass of writer. And if we then have in the data a triplet, one triplet, that this identifier that stands for Karel Čapek is in relation with this book that is identified by ISBN using the relation has written, we have the mapping to check writer and to book. So from this information we can basically joined the schema with the data, and we can infer knowledge out of it. So basically this is how we use the ontology to link the facts together using the ontology, because there is of course another writer that is not Karel Čapek but different one, but it's still linked to writer and so on, and we can really get a graph of facts that is using the ontology, using the schema here, link all together into one base of graph data. Yes, once we have the RDF, we need some language to work with RDF, because now we are in the land of graph data. So the RDF graph needs also graph-based language for querying. In this case, it is SPARQL. SPARQL stands for SPARQL Protocol RDF Query Language, and it basically is supposed to be used for RDF knowledge bases. So it allows to query using different variations. It somehow resembles to SQL query language select statement, but because it doesn't work with relations but with graphs, it has different syntax. So the construction of the query respects the graph-based structure of the data and enumerates using these variables and basically walks on the graph and allows to aggregate and so on. And unlike SQL that takes relation and returns relation, here SPARQL takes graph and returns relation. So this is not symmetric. We always get relation, but we start with graph. There are other similarities with SQL. For example, there is relational calculus used inside and other features. Okay, so now we have the ontology layer and the RDF layer and the query language for RDF. But we still need somehow to define the ontology and to provide the reasoning over the facts. And for this we need first the logic, the inference model based on some logic, and some definition language for defining the ontology. And this is what OWL stands for, OWL. And this is basically language for knowledge representation. using ontologies. And there are some subclasses of OWL, so there is some light version and full version, some intermediate version for description logic, and so on. So this quite rich family of languages. But basically what does it do is that OWL allows to reason about facts. So we have the ontology, we have the facts, and altogether using OWL we can reason about facts on top of some logic, like description logic. The first the first ontology and the first application basically of semantic web was the friend of a friend application, which is ontology, an application that allows or provides machine readable ontology for describing persons. So it is of course we see tools for putting friends into our neighborhood in applications of social media like in Facebook, but here it's important to say that this friend of a friend application of semantic web is not closed into some web application like Facebook. In Facebook we have everything proprietary and dedicated and closed, and you cannot export the graph of your friends or any people outside and make a database out of it, because it's closed application and it's not open, and also it is not general. It just has the fixed database schema. You cannot have your user defined data entity. You have a user profile, page, post, comment, and so on, but you cannot create your own completely new type. But in the case of RDF, you can do this. You are completely free, and it's open, and it's data level modeling of for example, social network, like in case of friend of friend. For example, it could be a short fragment of friend could be seen here, where we have again the web page about Tony Benn, and here we have the FOAF primary topic, that the person that we are describing here is Tony Benn. So, and it's not just a string, it's a name in the friend of a friend ontology. So it got different semantics here than it was before. Okay, so we have introduced or discussed some particular technologies that altogether could be viewed as technologies contributing to the semantic web, or making the notion of semantic web true. But the truth is that only fragments of these semantic web technologies are successful. For example, okay, the friend of a friend, it's not so big deal, but there is another very successful concept of semantic web using RDF, and that's linked data. We'll talk about in a while. But the whole World Wide Web is not semantic, because it cannot be just ordered, okay, let's switch from syntactic to semantic web. It's more that some pieces of the content on the web basically embed some semantically formatted information, for example, using RDF, or using completely different microformats like Google does. Google has its own standard for microformats that basically carries the same, so some semantics, and therefore Google is able to provide some rich querying capabilities as the ones we have announced in the beginning. So Google itself could answer a query, and the answer is not that it returns a particular web page, but it actually really answers the query, like with the houses in New York and so on. But this is heavily dependent on the information in the present in the microformat data. Well, as I said, solutions to to transform the syntactic web into semantic web is there are some reasons to switch. The first is better motivation. If these semantized pieces of data are favored by Google, for example, in the ranking, then it's a good motivation. It is also beneficial for the services, because if the semantic information helps people to find more complex queries, then there is another. That's the motivation for putting ontologies and semantic information into web. In the last discussion, I would mention the link data, which is the very successful application of semantic web part, and it is basically a set of best practices for publishing structured data on the web. And this is a huge topic, and we have other tutorial on link data, and it is a standalone subject, but it serves as a good example of what the RDF basically and SPARQL are capable of. So what the link data principles use? They use the URIs as identifiers for things, as unique identifiers. It of course uses HTTP, and mainly it uses the RDF for representation of facts. And using this, RDF powers link data to act as a higher abstract layer on top of some data repositories. So this is basically the idea. We have some data repositories hidden somewhere and having very proprietary specific interfaces, and these databases are not available using some unified interface, and that's why the link data layer could be created, could represent the data provided here, and to establish something like global data space in the RDF format. So this is the vision of link data, to providing unified interface to data, but the data itself is somewhere in their original repositories. So this is some middle layer for just publishing the data. One of the first link data application was DBpedia, which basically is the data view on Wikipedia. So we have Wikipedia, encyclopedia of many things, and the data is stored in the Wikipedia. So basically, that's this Wikipedia itself is the static is the syntactic web, because okay, it's formatted more structured. The formatting is more structured than just HTML, but it's still designed for presentation of information. The DBpedia, on the other hand, tries to or represents the data representation of Wikipedia. So in DBpedia, there is no formatting. There is only the data is extracted from Wikipedia, and then we can see records for the entities from Wikipedia like this in the DBpedia, and some browser like the public browser here. We can see the entity called Český Krumlov and the properties of this particular entity. So there are many of specifically defined properties that are in the namespace DBpedia all. So all of these elements basically live within this ontology of DBpedia, and the values are this one. So we can have some abstract about the city of Český Krumlov. We have linking of the city to the country, which is Czech Republic. We have elevation. We have different features. and some of the features are given in constant, and some are again given as a link. So for example, we have here a record about Vltava, which is a river, and therefore this entry is not a constant that doesn't lead anywhere, but it is again named entity that provides another linking. So we basically observe here the graph information, very rich graph information or multi-graph information, because all of these properties are basically different types of edges, because this is the one node, these are the other nodes in a graph, and this is the edges, the properties. So what are the properties of linked data? Oh, as we said, it's data space that is meant to be global, uniquely identified entities, and is built on simple set of standards that are basically just RDF, URI, and HTTP. So it's not so complex that it could not be basically used for practical applications. And there are also other features that basically respect the nature of web. In the web, everybody can publish data in the HTML format, and again in the world of linked data, also everyone can publish data in the linked data. Everyone can express comments on things and so on. So this is not something that is centralized. It's still a distributed data space. So, and that's why it can be maintained, because there is no maintenance basically. So everybody can contribute to linked data. And there was a project of open data that was powered by W3C consortium, and it tried to link different ontologies into one big cloud, and to provide and to open linked data to more and more applications and to more and more parts of the web. So at first in 2007, 13 years from now, it began like this. We had the DBpedia, friend of friend, as a couple of other ontologies and repositories, and then it in 4 years or in 2 years it expanded, and in other 2 years it's again expanded, and today another 9 more years ahead, and it's a huge cloud now. So the linked data activity or linked data application of semantic web technologies is hugely successful in this case. These are some statistics on the beginning efforts within the project. There are some millions of triplets, entities, and so on. It's not up to date today, and it is also quite obvious that the linked data is mostly useful in domain where there is required open information by law. So it has most applications in the government services. So if the European Union is obliged to publish data, for example from Eurostat, or also national governments need to release public data, the good technology how to do this is using the linked data, because all of the national and even European offices publish their data completely independently. There is no synchronization, and that's why the linked data layer is very needed and useful to basically interpret all of these partial repositories as a part of one global data space. So in this sense, it is very successful. There are other topics when talking about linked data. We can identify browsers of linked data, as we already saw the PUBI. We can use the search engines for linked data, and mostly we can create mashups on top of applications that use linked data, and basically the mashups are the mostly expected added value to linked data, because basically this unification of the global data space basically is what mashups expect. So this is the perfect application. We can see, for example, in the summary, we see that we have some dedicated databases, the linked data arc layer, and then we have different types of applications like the browser, search engine, and mainly the data mashups. And these linked data mashups are often based off some real maps, because, as I said, most of the data in the linked data cloud come from governmental or some public service sources, and these are bound to some geographic location. So it is very natural to provide different maps of anything, so to visualize the open data and the linked data in a form of some map-based aggregation of facts, like here. One of such application is the map of contracts, public contracts on this URL, and we can see on this map that there are some suspicious contracts that are somehow defined, that they have specific properties. Basically, how it's done is that these contracts are selected using this SPARQL query, and it's quite long, but we can see that the result of this query are suppliers of some suspicious public contracts of a state company, and the suspicious means that there were accelerated negotiations taking place. There were only one member in the tender, and there was a large budget of the project. So all of these properties together, when taken into the query, we get the result here. And that's it.